Yes, sir, you are live now.
So how will we know the questions? Where will they appear? In the
The questions you will see YouTube chat, sir.
okay, okay. So we will have to join that as well, I guess. Okay, okay. All right. So those who have joined the YouTube link, they may please ask questions in the chat box. We will have a look at that and then we will answer the questions one by one.
We still don't have any questions in the chat box as yet.
Yes, no questions. Sridhar has put that they can ask questions just to remind them. So let's see whether we get any questions. Good evening, Siddharth. Do you have any question? Okay, the question is, will the computer architecture book by David Patterson serve useful for the examination? Yeah, to some extent, yes, it will help you in understanding the basic architecture, but the entire book is goes much into depth of the subject. So maybe you can read through the just the initial chapters, which will be helpful not only from the more than from the examination point of view. It will be more useful for you to understand the complete ecosystem of HPC, part of which is the CPU. And these days we have multi-core CPUs, so those aspects will be helpful to understand from the Patterson's book.
Yeah. The other thing that I would like to add is that if you are especially not from an electrical engineering or computer science background, the first few chapters will definitely give you an idea of how these systems work. See, most of HPC users, if you think about it, they come from different domains and not from CS or EE in general. They are application scientists, but they need to have a good understanding of the hardware. And I think, as Mr. Kuvelkar said, the first few chapters should help you with that. I encourage all the other viewers also to put in their questions in the text box so that we can answer them. So there is one question regarding what is the applications of HPC with the scope for startups, and if you can identify a niche as aeroplane performance. So effectively, what I would like to say is that, see, every industry will have some sort of a need for simulation. Now, aerospace industry definitely has a lot of need for simulation technologies, in which that you can create uh, codes, CFD codes, or modeling and simulation codes broadly in general, which with which you'll be able to sort of then deploy these on HPC platforms. So essentially, you'll be able to have modeling and simulation codes which can scale very well and solve extremely large complex problems. So that would be sort of the niche. So you'll have to sort of identify what is a problem that you want to simulate, and then use your HPC skills to simulate that in a more complicated manner on these HPC systems.
To add to what Professor Shiva has said, uh, he's rightly pointed out that simulation, modeling, these are the fit areas for to be solved on HPC. And within that also, I mean, you have asked another question, prerequisite and skill set. So there are two things that one can do. One is that there are some available standard softwares, some of them are open source. They can be used for doing modeling and simulation if that is a need of that startup. It depends upon what they are into. Like you talked about aeroplane performance. So they are into things like wing design or something where it's a the CFD principles can be applied, wherein a solid is moving to a fluid. So there, the standard softwares can be used. That is one skill set that one can have. That is using how to use these softwares to solve a problem. Going one step further, in case they have some requirement where they need to write code, a parallel code, which is actually a big task. But there could be some things where or some situations where the standard softwares you have to do something beyond that what the standard software do, and maybe through scripting or through some parallel program that you want to analyze that data that they have generated or visualization of that. If there are any such things, then in that case the skill set would be ability to do parallel programming. That's what I would like to add to what Professor Shiva has rightly already said. Thank you.
Okay, so there's another question which is talking about dual CPU motherboards and server grade processors. Now, the question is a dual socket CPU more effective for scientific computing? Now, the way you have to look at it is how many effective cores that you actually get. Now, this is a sort of a really, in between tricky question. The reason why I say that in between tricky question is it also depends on the quality of that motherboard. So remember that when these two dual socket chips are there, you have two processors sitting on them. What really matters is how fast these two processors can communicate, how fast they're connected to the memory, and obviously the effective number of cores that you have. So it's not a simple straight answer. So you might have a situation where a single socket 128 core machine is better than a dual socket 264 core machines, right? So there's a possibility that that is better. So it all comes out to the specs of the motherboard and the specs of it. But obviously, if you have two sockets, that means I can, and if it is the two of the latest sockets, I can then populate it with the highest number of cores which are there in a CPU. So then I can, let's say in the market you have a 128 core CPU, which is the top seller at this point of time. So you can have two 128 core CPUs. Then effectively you can have 256 core CPUs, and then that's good. Now the second question related to that was, is ECC required in HPC computers? See, ECC is preferable to have error correcting codes. Basically, what it does is that if there are any sort of errors which are propagated in the memory, it is better to have ECC memory. But ECC memory, essentially what it does is it pushes up the cost of the entire system. So there's not really a lot of harm in taking non-ECC memory, but I think having ECC memory is better. And yeah, so essentially, yeah, desktop processors, you typically do not end up with ECC memory because the applications that run on desktops are typically not very critical. At the server end, you have critical applications, and that's the reason why you tend to use ECC. If Mr. Kuvelkar would like to add something to this.
Yeah, sure. So the first thing to be noted is that when you have a machine which has got a motherboard with dual socket, then both these CPUs, both these sockets will act as a shared memory computer with reference to the total memory that you have. So essentially, all the cores of both the processors, both the CPUs put together, they will have an equal access to the memory. When I say equal, means each of these cores will be able to reach or address any of the memory location in the entire memory that is present. However, as Professor Shiva has said, internally what happens is within every CPU, that is every socket, there are multiple cores, and every core has typically a private L1 cache, a private L2 cache, and a shared L3 cache among all the cores within that CPU. That is the way each CPU is. Similarly, the next CPU will also have multiple cores, each core having his L1 cache, L2 cache, and a shared L3 cache. Now, these main memory that you have is now one level above. You can say it's not a cache as L4, but a next level memory. Let's say we'll call it as level 4 memory, which is common to both the sockets. So as a result, now you can see the hierarchy. The main memory is common to both the socket. Within a socket, there is a L3 cache which is common to all the cores, and every core has its L1 and L2 cache. So this is the kind of hierarchy that you build. And when you have a single socket, then all the requests coming from the CPU, there is no contention with any other CPU when it tries to reach the memory. But when you have two sockets, it's possible that both the CPUs simultaneously will try to reach some part of the memory. And in that case, if both are trying to reach the same DIMM memory module, then there can be contention. This contention never comes on a single socket CPU motherboard. Having said that, in a supercomputing system, typically the architecture uses cluster, and a cluster is a collection of nodes connected by high-speed network. So as of today, the most popular architecture for a node is a dual socket motherboard, for a simple reason that this gives you a best price point between the number of nodes that are required vis-a-vis the power that you get from the cumulative power, compute power that you get from them. Coming to ECC, Professor Shiva has rightly pointed out that typically server ECC is present only in server class motherboards. It's not present in desktop motherboard. Rarely, if you have a graphics workstation or something, that kind of desktop, then possibly it will have ECC. The advantage of ECC is that the chances of your computing system running uninterrupted increases with ECC. Not that non-ECC memory is also not that non-ECC memory fails, but it's like having an insurance or having an added feature which gives you a better chance of continuity of your computing system running for a long time. And since the supercomputing systems need run jobs that go on for hours, it is you will find that most of the nodes in most of the supercomputing clusters, the nodes have got ECC. Of course, it comes with a price, but then as compared to the overall price of the big supercomputing system with various component, the incremental cost of ECC becomes less. But if you're buying just one node, then possibly it may become significant. Thank you.
So there's another question. It says, is there any way we can optimize an application to collaborate in dual CPUs using parallel programming, using C or even assembly? See, we are already doing that using C, in the sense that when you look at OpenMP programming, or if you were to look at pthreads, we are essentially collaborating between these dual CPUs. As Mr. Ashish said in the previous response, a dual CPU motherboard will essentially behave like a shared memory machine, right? So effectively, the entire memory bank, addressable memory, is visible to the code, and if it's the OS will sort of actually see these dual CPUs as sort of a multi-core. Let's say that you have two CPUs which have 64 cores each. The OS will see it together as a 128 core shared memory machine and will start scheduling things over there. You can do a little bit of what you say, optimization, or rather a little higher level of optimization, by sort of pinning certain processes or certain threads to certain cores and certain CPUs. You can do what you can do, some sort of process of pinning. This we will cover in some advanced topics towards the end of the course. So in effect, if when you write a parallel program in OpenMP, or if you're slightly doing it in a slightly lower level of programming like pthreads, which we don't cover in this course, you're already collaborating between these dual CPUs to do this program. Thank you.
Yeah, to add to what Professor Shiva said, assembly I would not recommend, because what happens is assembly program will typically run on one core of a CPU. And when you have a multi-core CPU, essentially there has to be a framework which is above this program, which then schedules is across the cores. So theoretically speaking, yes, like C, you can write the code in assembly, but then this code written in assembly will have to be then used as a program unit, which is further scheduled by pthreads or OpenMP to run across the course. So assembly is not recommended. C is good enough. And as Professor Shiva said, either you use OpenMP or MPI, they will be able to harness the compute power cumulatively offered by all these cores put together. Thank you.
So if we request the viewers to make any questions, put any questions in the chat box. And if we don't receive any further questions within the next couple of minutes, then we might close the session. Okay, thank you. So there's another question regarding mini NVIDIA DGX systems, which is used in LLM applications. Can systems custom built using many CPUs and GPUs match the same performance of a proprietary DGX machine? Well, yes, it definitely can. So you can always add up a lot of GPU cards or even lots and lots of CPUs and make a machine which in performance will be equivalent to a NVIDIA mini DGX system. The question that you need to answer is that how efficient it will be in terms of power, how efficient will it be in terms of space, because these mini NVIDIA DGX systems are kind of really engineered well and compact. Also, what is the cost of putting together such a machine, which is going to give you the same performance as the NVIDIA DGX? So you understand that the NVIDIA DGX system is quite expensive because it has multiple GPUs. It's been engineered to a certain level, but you theoretically you can always put together a machine which is going to be as powerful as that by having multiple compute nodes or multiple GPUs. But you'll have to figure out what is the efficiency with which you're going to have that computation.
To add to what Professor Shiva said, uh, if you are trying to make a system similar to DGX, like a box-like thing, then the effort is huge. I mean, it runs into thousands of man-hours because it's, as he said, it's a quite a complex system. However, there is another way that people generally do to get the same compute power is through cluster. Because cluster, the building block is a two CPU box. Again, money is what you should have. and but the power efficiency of such a system, the space that it takes is going to be quite big. So you have to, if it's for a purpose of learning, or if it's purpose of doing things on your own, then it is one can always go and build a cluster which again will have to be suitably scaled up in terms of number of nodes that you will need uh, to match the compute power of a NVIDIA DGX system. Another thing to note is that the NVIDIA DGX system comes with its efficient software stack and open other softwares that help you in making use of that LLM based applications to develop or to train or to run the inference engine. When you do build your own system, then you will have to depend upon the open source softwares, because developing customized software for such a system again will be very cumbersome. So to the short answer is, what, yes, you can do it, but you have to think about the efforts that will go in, and what is the purpose of doing so. Over. The next question is rack-based architecture in cluster that contributes to lower cost. Okay, so when you say rack-based, even NVIDIA DGX systems also go in rack. See, a rack is typically, I guess you are meaning a cabinet. So a cabinet is typically 42U, and the DGX system is something like 4U or 5U. So whether it is a DGX system or whether it is a cluster, which is a collection of nodes, they are essentially come in 1U, 2U, or these days, like the Param Rudra system that CDAC has built, it is of half U width. So in 1U, you can put two of these nodes. So the rack is a mechanism by which you can optimize the space, but then you are also concerned with removal of heat, whose density becomes high, because in small space you are putting too many CPUs. So the lower cost of cluster comes from the volume, because there are multiple vendors that make nodes. There are multiple, you can say, the nodes are based on multiple architecture, like AMD make AMD based, Intel based. Within Intel, there is Sapphire Rapid. That there are many, and they keep coming. Like Intel will have a new CPU every few years or something. So you can pick and choose whichever suits your budget. So in that sense, the advantage of rack is like it's like compactness, but the basic elements remain the same, that is the nodes, and the lower cost comes from the fact that NVIDIA has it has a distinct advantage of having a proprietary architecture with a complete out of a box solution which contains everything, whereas a cluster is will take more space than that, but it will because it is a multi vendor sourced, the costs are lower. But again, as I mentioned, the cost of ownership is something that you need to check when you compare the cluster architecture in rack versus NVIDIA DGX system.
Yeah. The one more thing that I would like to add is that one of the premium things that we always pay for is space. You might think that a desktop doesn't consume enough space, but as Mr. Ashish Kuvelkar said, that the Paramrudra, for example, in a one use space actually has two compute nodes. So if you think about a 42U cabinet, it actually has 84 distinct computers. Now, if I take 84 desktops, you can imagine how much volume that was going to take in terms of real estate. So that adds up to the cost a lot. The other thing is cooling. If you have rack-based systems, while they are dense and heat removal is a problem, but you can remove heat from them in an efficient manner. Whereas if you have desktop-based system, removing heat from them, 84 desktops for just one 42 unit, it's very difficult, right? So then your cooling costs, your running costs of your cluster become extremely high at that point of time. So you might not spend that much money in building the cluster, but running it, you'll spend way more money compared to in a rack-based solution. Thank you. Okay, we thank you for joining this nice live interactive session. And we would like to thank the audience for joining in, and also all the members of the instructors of this course who joined in on Zoom. We thank everybody, and also our NPTEL team who has been working tirelessly to support this online course as well. So thank you all. And with this, we will close today's session. Thanks.
There is one question
Oh,
which I
okay.
will
There's
answer.
one
Yeah,
question.
I will just
Yeah,
answer.
please go ahead.
Yeah. So the question is, what are the notable HPC deployments or initiative in academia, government, or industry? Currently, Government of India is running a program called as National Supercomputing Mission, in which there are four verticals. One is the deployment of systems. As of now, about 16 supercomputing systems have been deployed across India, and which includes academia, which includes government labs. As far as industry is concerned, there will they are used by some specific industries like oil and gas and many other, whose details may not be available in public domain. But if you want to know about the National Supercomputing Mission, please visit this website nsmindia.in. I think I will be able to put it in the chat. Let me just put it the website name nsmindia.in, and you will get for details on National Supercomputing Mission. Yeah, you can click on that nsmindia.in. Okay, that will give you a complete idea about which are the places where they have been installed, what are their capacities. All those information is available on this website. Thank you. So we will close here. I again thank the audience as well as the NPTEL team. They are managing so many courses and they are really helpful. So thank you, NPTEL team. Till we meet live again, goodbye from us.
Thank you. Bye.
Thank you, sir.